Alright, this is Mr. Gillum, and today we're going to continue on with a few more theorems of similar triangles here. And yesterday we talked about the altitude, and we talked about the angle bisector, I believe. And so today what we're going to talk about is the median. Now it's been a while since we've constructed medians, but as a reminder, a median takes a segment from a vertex and it goes straight from the vertex to halfway in between its opposite segment. All right, so there's no special relationship on a median with the angles, but it does divide its opposite segment into two equal parts. Okay, and so now we have the same type of abbreviation that we did yesterday as far as this theorem goes. Similar triangles have corresponding medians is the new word, proportional to corresponding sides. So it's very, very similar to the other two theorems that we learned yesterday. As far as what we're going to be doing is we're going to be comparing the segment that is connecting C to AB and the segment that's connecting Y to WX. All right, and it's very similar. We're going to compare that median line. The CD right here, this guy, compared to YZ should also be proportional to the corresponding side, specifically AB to WX. All right, that's how we're going to set up our proportions for this one. And it's very, very similar to yesterday, just hard to remember all the different names for everything. So it says, in this case, find the value of x. Now, just looking at the diagram, it doesn't say there's any medians, but when I look at it, I see that T connects to segment at RS, and it makes two equal parts. So that tells me that it's a median. Okay, it tells me that that's the median. And in this case also, W is connected to UV, and it makes equal parts. Right there. So what I'm going to do is I'm going to say, okay, let's compare this here. It might not be obvious right away, but the two angles right here match the two angles right here, one angle and the one angle. So it looks like V would reflect onto S, WT, and U would be R. Now don't forget that this median does divide it into two equal segments. So I could also say that this length is X, and I could say that the entire length is 2X. And over here, the same way, at this side, this part is 3, and this is a median. This is also a 3, and so my total side length would be 6. So if I'm going to compare the two similar triangles, and I don't have enough for, well, I know they're similar because they're angle similarity, but I don't have enough sides to compare or anything like that. What I can do is I can compare the medians. So I'm going to compare from left to right. 13.5 compares to 9. And the entire bottom part, 2x, compares to 6. All right, now when I cross multiply, looks like 13.5 times 6 is 81, equals 18x. And now I'm just solving for my variable here. So x, in this case, if I reduce this, we get, let's see here, 6, 27, 2, 9, looks like we have 9 halves in this case. X equals 9 halves. So I don't need to plug the 9 halves in anywhere. It's not, the 9 halves doesn't represent this whole side, it just represents x, and in this case, x is the part we're looking for, so I know that my missing side length would just be 9 halves. Okay, my missing segment length, SP, would just be 9 halves. Okay, so very, very similar to yesterday. Once again, we're comparing this median line or this altitude line, this angle bisector line, to a segment on the other corresponding triangle in the corresponding area. So very similar to yesterday, only one example today. Very similar, just try to keep in mind the names of everything. The median ends up in the middle of the segment opposite of the vertex. That's the only, it's just very similar to yesterday, except for that fact that it's the relationship is in between the segment. Now here's where things change quite a bit, and this could be a little confusing. It's called the triangle angle bisector theorem. So triangle angle bisector theorem. And an angle bisector of a triangle also divides the side opposite the angle proportionally. So now all of our theorems so far that we've been talking about have been comparing this line that connects a vertex with its opposite segment. This one's a little different, okay? Now what we're going to compare is, if this is an angle bisector, we're going to compare Km to Lm, and we're going to compare JL to JK. All right, so we're not actually using this value at all. All right, we just know that there's a proportional relationship. If I bisect the angle, there's a proportional relationship between this part and this part, each side of the angle bisector, and the long side next to. All right, we are not using this middle distance or length for anything on this theorem in particular. All right, so let's take a look here at some examples, and I have a few more examples of this one. It says find x, TR bisects QRS. So this is an angle bisector. It looks like there was in my diagram, there was a missing part there. Okay, so since it's an angle bisector, it tells me that this length compared to this length, all right, is comparable to 6 and 14. All right, so that's what I'm going to do. I'm going to compare. Now, because I don't really know how far this distance is, but I do know the whole distance is 18, I'm going to represent this by 18 minus x. So what I'm comparing is x to 18 minus x. I'm comparing it 6 to 14. And now for the sake of keeping my number smaller, I'm going to go ahead and reduce this fraction right now instead of later. And now I'm going to cross multiply. 7x equals 54 minus 3x. 10x equals 54 when I add 3x to both sides. So I know that x equals 27/5 when I reduce. All right, so in this case, x would be 27/5. So one more time, this is a little different because I'm not using anything with this line connecting a vertex to its opposite segment. All right, I'm comparing the portions of the segment, the x with the other side and the 6 with the 14, and that's what's going to help me to find my distances there. Okay, let's take a look at another one here. Once again, find x, and it looks to me like because it's labeled that these angles are the same, that this is an angle bisector. And so once again, the angle bisector, the triangle angle bisector theorem says that there's a proportional relationship between each part of the segment that it splits. So the 4 can be compared to the 6, and the x can be compared to the 13. All right, and once again, we're not using any measurement. We don't need any value right there for this theorem to work. So I'm going to compare 4 to 6 and x to 13. And so in this case, it looks like we have 52 equals 6x. So x equals 26/3 when I reduce. Okay. So once again, the only thing this is, well, it's kind of a big deal. Triangle angle bisector theorem is important because we don't need the length of that connecting segment from the vertex to the opposite segment like we do on a median or an altitude or an angle bisector for those other theorems. Okay. And one more example here. Once again, I have, this is actually supposed to be an angle bisector. I know they left out that marking, so make sure you do mark it on there. I'm an angle bisector. I don't know the length of this, so this tells me I'm going to use my triangle angle bisector theorem. I'm going to compare x to this portion right here, and this portion can be represented by 20 minus x, and I'm going to compare 14 to 11. Let's compare x to 20 minus x and 14 to 11. 11x equals 20 times 14. Let's see here, 280. Minus 14x, and what I'm doing is I'm distributing the 14 to both parts of my 20 minus x, and now I have 25x equals 280, and of course it doesn't work out perfectly again, so we're going to say x equals, let's see here, 280 divided by 5, good old-fashioned long division. It's like it goes in 56 times, so 56/5 in this case. Nice fractions today, I love it. That's fine right there, just how you have it. So today we have one theorem that is very similar to yesterday's, where we need the length of the vertex to the opposite segment. And we have one theorem that we don't even need the length here, and we can make comparisons between the segments that it separates it into. All right, so that's it for today.